Okay, yeah. Great. While he's setting up, just thanks for the wonderful conference. It's been just amazing hearing all of the rapid recent progress. And, I feel like this field sometimes comes in bursts of progress and then things go slow. And I definitely feel right now that the field is in a burst of progress. So it's great to be able to keep up on this stuff and learn so many new things. What I am going to be talking about is indeed dipolar synthetic dimensions. Didn't even need a something something, it turns out. Um, so apologies if you've heard this. I did give a similar talk. Many of you saw in the audience near London and at a bed and breakfast near London a few months ago. And I was going to skip all that stuff and just sort of only tell you about new stuff. And then I remembered that not everyone was there. And then also probably some of you have memories like mine where you're not going to remember everything I said 4 months ago. So I'll review some of that stuff, but I am going to talk about new material as well. And I'll tell you about what a synthetic dimension is and what's great. This picture here is really supposed to be a picture of nanobots, I think is where I got this from, with the idea of having programmable matter that you type into a computer, you want a chair, and your nanobots build a chair. We want to do the same thing with quantum matter. And so I'm not really going to dwell on that perspective, but that's one of the reasons we like these synthetic dimensions, that they give us exquisite control, really full control over the internal states of these molecules. And at the end of the day, that's probably one of my biggest motivations for doing this research. We can talk about lots of interesting applications and quantum simulation, quantum computation, all of these fun things. But really, at the end of the day, I just have an intrinsic belief that getting more and more coherent control over complex quantum objects is an exciting scientific frontier, and who knows where this will lead. And this is just a great example of a step along the way. But before I talk science, many of you probably don't know that I actually went to school in Warsaw, um, Warsaw, Ohio, a town of 624 people, so it's a little bit different. And it turns out it is named after the capital of Poland. I'm not sure they actually taught us anything about Poland in high school because of the wonderful American education system, but I know now. Anyways, as much as I hate to talk bad about my alma mater, this Warsaw is much nicer. So thanks for the invitation. So here are some pictures of synthetic dimensions. Synthetic dimensions have now been realized in a lot of different quantum systems, from photons to molecules to Rydberg atoms to momentum space lattices. And for a really nice review, you can look at this article from a few years ago by Ozawa and Price. For a less nice but much shorter and sort of easier article, we had a Physics Today article in April that you can look at for a reference. And one reason I'm putting this up here is actually the type of synthetic dimension that I'm going to talk about today with molecules or Rydberg atoms. They're sort of morally equivalent at some level. These didn't even exist when this review article was proposed. Actually, this review article might be the first place that proposed them in a sort of throwaway sentence somewhere right in the middle of the paper. So the field's moving rapidly, not just for molecules, but also this general field of synthetic dimensions. And today I'm going to first start telling you about the one particle physics. That's really where the synthetic dimension lives, and we heard a little bit about this from Michel and Meshko yesterday. And then I'll tell you about really where most of our focus has been, which is the effect of interactions and how they couple to these synthetic dimensions. And here I'll really be telling you about something very new that we're excited about. We just had a preprint a few weeks ago out on this, and it's this idea of something called parastatistics. And this is a new type of particle that emerges as an excitation in these systems that is neither a fermion or a boson, and so you immediately say it's an anion. It's actually not an anion either, and so I'll tell you exactly what's going on there. All right, so what's the idea of a synthetic dimension? Oh, before I get going too deep, feel free to interrupt me. If you have a question, raise your hand. If it's too hard for the organizers to bring you the mic, I'll just repeat the question to keep things going, but I'd rather just have a discussion here, and I'll make sure we hit the highlights. So what's a synthetic dimension? First off, what's a real dimension? Just think about a spatial dimension. You have some degree of freedom, some position that labels where a particle is, right? And so maybe the simplest example to think about is to kind of discretize space, or think about putting a particle in a lattice if you're a solid state physicist. And now in this drawing, there are sort of 4 places that this particle can sit, at least in the single band limit. There are 4 places this particle can sit. You have a 4-dimensional Hilbert space. I'm sort of drawing it vertically here. And so maybe if you spend a lot of time with molecules, this reminds you of the state space of a molecule. So I could pick out 4 different angular momentum states, for example, and use those as my Hilbert space. And that's the same picture that Misha drew for us yesterday or the day before, whenever it was. But to have 2 quantum systems be equivalent, we don't just need that they have the same Hilbert space, they also have to have the same Hamiltonian. So what's the Hamiltonian that describes a particle in a real space? Well, the particle can tunnel from site to site, right? There's some coupling to go from one site to the other, and we can ask how to engineer the same thing here for the molecules. But you actually know how to do this by turning on microwaves that are near resonant with these different transitions. This actually is mathematically identical to a tunnel coupling when you go to the rotating frame. So in the rotating frame and making the rotating wave approximation, tunneling is exactly the same as a resonant microwave. You could ask, is the rotating wave approximation any good? But for the sort of parameters we're going to look at, this is probably accurate to better than 1%. So you really have this one-to-one mapping. And because this is not a harmonic oscillator, it's a molecule, it's a nonlinear spacing, each of these transitions has a different frequency. And so you can use different microwave frequencies to drive different transitions. And maybe you don't even need polarization control because you can just spectroscopically pick different transitions. And so you end up getting a sort of full controllability in this internal space of all of these tunnel couplings. So you can just program in whatever sort of geometry you want, whatever sort of band structure you want. So here's a slightly more realistic depiction of a molecule as a rigid rotor. We have angular momentum horizontally, energy vertically. It looks like they're equally spaced energies, but of course in reality they're not. And we can do all kinds of couplings here. So if I pick out these states that sort of are in this bottom left to upper right diagonal, then I can couple the nearest neighbors, and this just looks like a one-dimensional chain. But I could also pick a set of states that has 2 one-dimensional chains right next to each other, something like this box, and now I've made a ladder system, right? So I have 2 chains that I can move vertically or I can move horizontally between the legs of that ladder. Maybe more interestingly, you can do things like periodic boundary conditions. You can make a ring, and you can even put a flux through this ring, because the tunneling phase is also controllable by the phase of the microwaves. So you can put on gauge fields. You can make all of these things time dependent, only limited by the control of your microwaves. And microwaves are fairly easy to add lots of them and control. So the other thing you can do is by detuning these different tunnel couplings, detuning these microwaves, it's like adding an on-site potential to your synthetic dimension. So you can also put on a sort of arbitrary potential landscape at the same time as you control your geometry. All right, and something you get for free is this synthetic imaging, a sort of synthetic quantum gas microscope. You can measure what state am I in, right? That's actually very powerful, and one of the reasons I think these are so nice. If you want to see an edge state or something that's localized in this synthetic space, you sort of get this resolution that you can resolve the population of each of these states for sort of free. You know, you don't have to have high resolution real space imaging to do it. So these are all reasons that we like these systems and why we want to do physics here. And so there is a very popular example to use in synthetic dimensions known as the Su-Schrieffer-Heeger model. It's the simplest example of a topological band structure. I'm actually just not going to tell you about it because I think many of you have heard me tell this story a few times, but there's some simple weak, strong, weak, strong, weak, strong. It gives an interesting topological band structure and topological edge states, and actually in something that is almost a molecule, this has been experimentally observed. So in Rydberg atoms, which is basically a molecule of a positively charged nucleus bound to a negatively charged electron, just a really big one. Tom Killian and Barry Dunning at Rice University used the states listed here to realize that band structure and then spectroscopically probe the edge state. So I'm happy to tell you all kinds of stuff about that. It's super cool. I actually think there's a lot of unexplored stuff here. Because do you recognize if I just did this with 3 levels, if I have a weak coupling between the bottom 2 and a strong coupling between the top 2, what this is? So this is Su-Schrieffer-Heeger. But a 3-level Su-Schrieffer-Heeger is something that quantum opticians love. Misha wants to answer. It's CPT, coherent population trapping, or electromagnetic induced transparency, or Outler-Towns. It's this kind of 3-level system, and this is something actually Hannah was asking me about at this last workshop. So I think this is a really interesting idea to explore, and I think a lot of the physics that you get from this 3-level scenario, where you have a weak and strong coupling, typically we require a really strong ratio of strong to weak coupling to get the kind of physics we want. In this sort of many-level setup that we have here, I think you can actually get the physics with a much weaker ratio of strong to weak coupling, and the effects are instead protected by the topology. So that's something that I'm very interested in understanding better, and if we can exploit this. But that's not today's talk. Instead, what I want to do is move on and ask, when I have more than one atom, what happens? Or more than one molecule in this case. So I'm going to start this story. We've studied this a lot. I'm going to start this story by continuing to tell you a little bit about the experimental progress in Rydberg atoms, and then move on to the molecules. And so the Rydberg atoms, we're going to think about them as essentially the same as the molecules. And so how do they interact? I have some set of states here. I'm just labeling them by this index n, and n+1, n+2, n+3. How do they interact? Well, I have a dipole-dipole coupling. I have a d dot d. Each of these d's can raise or lower my angular momentum by 1 unit. And so I could have in principle, I could have all the interactions where one of these goes up or down, and the other molecule also goes up or down in this sort of synthetic dimension. But when you think about energetic considerations, the only resonant processes are going to be when one goes up, the other goes down. And moreover, it's really only when you have n+1 that you go to n+1 n. That's guaranteed to be resonant, and it's the only process that's resonant. So what you should have in mind is only this flip-flop process is sort of controlling everything. That's our interaction. It's slightly more complicated in Rydberg's, so you can audibly boo Rydberg's in this audience. Some of you already have. So, that's one reason we don't like Rydberg's as much. Maybe the interaction structure is not quite as nice. But they have done the experiments already with the Rydberg atoms, and so this is Bryce Gadway and Jake Covey at the University of Illinois. They've made rings using this particular set of Rydberg states if you care. If you don't, you can just think about it as this diamond. States 0, 1, 2, 3, 4, 0, 1, 2, 3 that are coupled with microwaves in the way that I described, and now we let them interact. And this is in a tweezer array, a one-dimensional tweezer array, where they can do local imaging as well as the synthetic dimension. So we have real space interactions plus this synthetic dimension. And here's what they observe. So they start the molecule, atom, and this is the mistake of trying to combine both of these things in one talk. They start their Rydberg atoms in the 0 state, and here this data is just for a single Rydberg atom. So it's going to start in the state 0, and then ask yourself what you expect it to do, looking at this diamond over time. If you just release it, let's just think about the non-interacting case. That's what the results on the screen are. I'm going to go to 3 and 1 in a sort of equal fashion if there's no gauge field, and then they'll coherently interfere in this 2 state coming from the 1 and 3 states. And so this is the data of the populations in the 0, 1, 2 states as a function of time, and you see this is exactly what happens. I start in 0, that decreases, I get a little bit of population transferred to 1, the 3 state isn't measured, so the population is presumably equally split between 1 and 3. That's why these populations are lower than the 0 state maximal population, and then it gets transferred to this 2 state. Things coherently interfere. What's going to happen when I apply a gauge field? So now the 2 paths, 0, 1 to 2 and 0, 3 to 2, can destructively interfere because there's a phase difference. And so they go and do the experiments, they apply the gauge field, and this is exactly what they see. So now you're still getting these nice oscillations where the 0 population starts to dip down, looking at this right column. You get some transfer into the 1 state, but you see there's, when the gauge field is pi, so you have perfect destructive interference, nothing is transferred into the state 2. Right? And if you do a gauge field in between, some population is transferred, but not all. And so this is really telling that you have nice coherent control over these 4 levels and are getting all the interferences that you want. And also, it's just beautiful. You can turn on this gauge field just typing it into Mathematica or whatever you experimentalists use to control your experiments. So you just type in, I want a gauge field, and it just pops up a millisecond later, right? And it was amazing. I was actually at Illinois visiting them when they were doing these experiments, and we could really go back and forth with lots of ideas and just see how things worked. So very cool. Okay, of course, that was single particle physics. One of the big goals here is we want to do many body physics with this, and so this is at least approaching many body physics. The top line is going to be single particle physics, what we just saw. Second line is 2-particle physics. You have 2 particles and 2 traps. And the bottom line is 6 particles and 6 traps. In principle, nothing prevents them from going bigger, but, technical, blah, blah, blah. Okay, so we see some interesting things here already. As you turn on interactions and you go to the pairs of atoms, the dynamics clearly becomes more complicated. It's not simple oscillations. Maybe it's kind of chaotic looking. And the left column versus the right column is just the interaction strength to the synthetic tunneling. Weaker interactions on left, stronger on the right. And you see actually that as you turn up the interactions even for the pair, that dynamic slows down. And then you can go to really strong interactions, and now all that chaotic dynamics is kind of washed out, and it's just, so 6 atoms, it's kind of washed out. And when you go to really strong interactions, everything's just frozen. Nothing moves. So this is sort of a self-trapping phenomena. It's a dynamical self-trapping where the system at strong interactions is just getting stuck in that initial state. That 0, 0, 0 state has, if you don't have the synthetic tunneling, if you only had interactions, it can't do anything. Remember, the interactions are this flip-flop thing, but there's nothing to flip-flop with. If I'm in 0 and my neighbor's in the 0 state, I can't do anything, I'm stuck. And so that's really all that is. And so you get this kind of dynamical self-trapping, or this is a very simple type of what we call quantum strings. So if you think about having sort of one real spatial dimension horizontally, a synthetic dimension vertically, you're going from, at weak interactions, a system that fills out the whole 2-dimensional space. So when you turn on interactions, it gets stuck. And so it can't fill out that whole synthetic space. You get stuck in whatever your initial state is. This is a very simple type of synthetic string. There are much more interesting types that we've studied. If you care, there's a big list of references where we've done a lot of quantum Monte Carlo, DMRG, mean field theory, and we're working on some effective field theory treatments of these transitions, which are surprisingly fascinating. Okay, so that's kind of the status of where things are at experimentally with Rydberg atoms. But of course, this is a molecule conference, and so I want to say a little bit about why I'm so excited to do this in molecules as a next step. And so I know Simon, for example, has a lot of the ingredients to do this. Simon has these beautiful magic wavelength traps and has access to multiple rotational states. And so now this opens up a whole new world for us, because the molecules actually have many more stable states, many more accessible stable states in the rotational states and hyperfine states than you do with the Rydberg atom. The coherence is excellent in terms of being very long-lived coherence, but also even the coherence time to interaction ratio is very good. And one big reason is that in Rydberg experiments, when you're in a tweezer, you actually have to turn the tweezers off as you do all of the dynamics, because the Rydberg state's anti-trapped by your tweezer, and so it would just sort of get blown out, and so they don't live that long. You don't have that much time to do your experiment. Maybe in some new experiments, they can get around that to entrap the Rydberg states, but that's very, very much an undemonstrated feature so far. Also, the interaction structure, I alluded to this with molecules, is more natural than it is in the Rydberg atoms. You get very nice sort of, quote, local interactions in the synthetic space. And you can combine it, maybe most importantly, what I'm most interested in at a sort of fundamental level is you can combine real space and synthetic space motion. So with the Rydberg atoms, interactions are so strong, these Rydberg atoms don't move around at all in the time of the experiment. You can't let them or else things would be ruined. For a long time, I thought the same thing would be true with molecules. I was very pessimistic about letting molecules move around. But with the incredible advances in shielding in the last couple of years, I'm now becoming much more optimistic that we can do interesting things there. And so just to kind of, again, make this point, here's Simon's data showing these wonderful coherence times, observing the dipole-dipole interactions. I think it's very promising for the synthetic dimension application. I also, even without going to a big synthetic dimension, you could just take 2 of these internal states, right? So we have a nice spin 1/2 XXZ model like we heard about yesterday from Cal Miller. And that's already a wonderful problem, thinking about how that spin couples to motion. This is an important problem in lots of areas of physics. So you want to know how, if I put energy in a spin degree of freedom, how does it get converted to some other degree of freedom? So, superconductors, it's the phonons that's the glue. You can actually come up with sort of pseudo-spin models of the Cooper pairs and superconductors, or thinking about molecules, and you have relaxation of electronic state into vibrational states, or thinking about spintronics, where you have this kind of energy coupling. There are lots of fundamental questions where you want to know how spin degrees of freedom couple to nuclear degrees of freedom or motional degrees of freedom. And so this might be a real nice test bed for a lot of this stuff. Unfortunately, I have some results, but I didn't get them to Casper in time. We've been starting to study this. Let me tell you what these curves are. So just look at this bottom dash curve. That's the fit to the experimental data of the Ramsey contrast, which we've heard a lot about, the spin dynamic contrast decay. And this solid curve is the theoretical prediction if we assume all the molecules are kind of fixed in space. And actually the relevant comparison here is these solid data points, the solid squares and this solid line. And maybe surprisingly what you see is that the theory, the contrast decays faster than the experiment. So apparently including motional effects causes it to decay slower. And that's something that I think it would be fun to understand in more detail. We have some nice calculations based on truncated Wigner approximation that actually resemble very closely the experimental data. But there are other approaches, and I think it's a very timely topic for our community. Can we use these as quantum simulators to test these different approximations to spin motion coupled problems? Because it is a tough problem to solve. Motional degrees of freedom really are their own can of worms. Okay. All right, so I think that's fun, and then of course we can go beyond the spin 1/2 problem. If I have more than 2 levels, we can go build up a real synthetic dimension, and I think that's also a wonderful problem, but maybe I'll tell you more about that at the next conference. We're starting to study what new physics might that lead to. Okay, so in the last 5 minutes here or so, let me tell you about a real fun theory topic that just popped out of our studies of these synthetic dimensions, but also maybe let me pause and just see if you have any questions about this. So this is sort of, I've shown you the nice Rydberg experiments, hopefully given you this conceptual idea of controlling the internal degrees of freedom, and a little bit of perspective on where we might go with molecules. Crystal clear, crystal not clear.
I have a question.
Sure.
Well, you should just read it. Thank you. So you had, but there are other molecules out there, like tableting molecules.
Yeah.
So, I mean, is there any hope for those, or is there, in other words, like you had these regular structures in the lattice of those energy eigenstates, but if it's kind of broken a little bit, would that still be okay for your synthetic?
I mean, in some sense, you want it as broken as possible, right? So all the degeneracies and things that you have in the rigid rotor spectrum, if you don't want to have to mess with really accurate polarization control like Sebastian showed, then you want to be able to just select out different transitions by energy. And so the ideal case is there are no degeneracies in your spectrum for that. Now, other types of molecules are probably pretty interesting because they can give you different interaction structures. When I talked about the interaction structure that you'll get n+1 going to n+1n, that really assumes that you sort of have different angular momenta quanta for each of your states. But when you start doing things like loops, now it gets more complicated because maybe you can have exchange from one side of the loop to the other when I think about the interaction structure.
So there's definitely more.
I think it'd be very interesting to think as we go to more complex, not just these 1D chains, what can different molecules offer? Yeah, that's a great question. Misha, did I see you have a question? Me too, yeah.
Yeah, so I was thinking, instead of listening to your talk, I was thinking how to explain. Basically...
What country are you from?
Sorry.
This is a Russian-style question coming, I feel.
So how do you understand CPT topologically then? Because SSH has topological features.
Yeah.
Then I remember this article of Berry, that actually Berry discovered in like 87, that every 2x2 matrix has topological features. That if you go around degeneracy, a factor from linear algebra that should have been known like 200 years ago, he kind of popularized it in 87. And then I thought, is it correct way to understand like CPT that I write it as 3 by 3 matrix, and I go around degeneracy, pick up a phase of pi, and if I make it longer, then it kind of the same thing that happens, except the bulk, and then kind of that's kind of the topological analogy, or is it wrong?
I think the honest answer is I'm not sure. I have not thought about interpreting CPT in particular in this way. I've thought a little bit more about the outlier towns and sort of think about it, but of course it's all the same. Yeah, I mean, I would say the connection's not clear to me. The big thing is, so in CPT, what role does the sort of strong to weak coupling ratio play? Right? Where do you need a large strong to weak coupling ratio? Actually, I'm having trouble remembering how it comes into play there.
Well, the strength of the coupling is the elements of this matrix that
Sure.
You can go around the degeneracy with it, but yeah, we can talk.
Yeah, yeah. Maybe we should talk. I would really like to understand this better. And so when I'm saying that I think that you can basically replace this large strong to weak coupling with some topological features, that's really a conjecture. I haven't proved this yet. This is something that I believe is true, and I can give you examples where there are connections here, but I don't know if it's generally true for all of these phenomena.
Thank you.
Yeah.
All the time is already running.
That's the countdown to the question period, is that right?
It's running up. Yeah.
Okay, we're in the question period.
Already in the question.
Okay. Then let me give you the abbreviated version of this, but if it's okay, let me take 1 minute since I had some questions. Okay, so parastatistics is this fun theoretical thing that I want to tell you about because it does occur in the system and someone should go measure it. So first off, you've all been led to believe, you've been lied to by the man, that only fermions and bosons are possible. Why do you believe this? I will regurgitate the textbook argument for you. When we exchange two identical particles, I have let's just take a two-particle system for simplicity. I have a wave function of coordinates x1 and x2. I swap them, and I'm going to get some new state. If the particles are identical, none of the observables can change. So what's the only way I can guarantee that? Well, I have to have the same wave function, except I could have a phase factor, right? Some phase factor r. Now repeat that twice, and what you get is that psi x1 x1 is r squared psi x1 x2 is r squared psi x1 x2. So what is r squared? It has to be plus or minus 1. The end. Except, what if there was some hidden internal index of your particles? What if, other than position, they carried some unobservable index? So if you exchange them, as far as you could tell, they would still be identical. Then this r no longer has to be a number, but it can be a matrix. And there are lots of matrices that square to 1. Okay. And maybe since I am in the question period, I will kind of leave it at that. Let me just say, if that's all you go by, all of your theories will be bogus. You still have to satisfy things like causality. Ideally, you want your particles to have some notion of free particles, not interacting. And those impose some additional mathematical requirements. Also, when you go beyond 2 particles to more, there are some other mathematical requirements. And understanding all of this takes some pretty serious mathematics. And we had to, in fact, develop sort of a new second quantization formalism and some new diagrammatic calculus to deal with this. But it's done, and at the end of the day, it looks very similar to what you're familiar with. Normally you'd say psi dagger is either plus or minus psi dagger psi. Here the only difference is instead of just plus or minus, you have a matrix that acts on these new indices, or actually a 4-rank tensor. But otherwise, you work with it like you would any other theory. It works beautifully, and the simplest example of a theory that gives rise to these is exactly a 3-level molecule system. Just take the sort of one-dimensional synthetic dimension with 3 states, or you can just think of it as a spin 1 model. Take a 1D chain. This is exactly solvable, and the excitations are in fact parastatistical in nature, not fermionic or bosonic. And unlike anions, this extends to 3 dimensions. So someone should go do that experiment and observe these for the first time. These are all my collaborators. Bryce and Jake did the interacting Rydberg experiments. Tom and Barry did the single particle topological band structures. Simon, the data I showed for the molecules was from Simon Cornish, and then this is my wonderful group that's worked on all this stuff. Thanks.
Thank you very much, Kaden. We have time for maybe one quick question still.
variables into quantum mechanics.
Yes, that's right.
Okay.
Yeah.
Good job.
Yeah. So more of a comment than a question, I guess. But
No, I was just wondering how is it different, and so whether you can call them quasi-particles actually.
these are quasiparticles.
Yeah, if you
so
integrate
so the
them.
analogy here, probably what you know very well, is what would happen if I only had 2 levels instead of 3. Then you do a Jordan-Wigner transformation, and the sort of nearest neighbor, at least XY model, maps to non-interacting fermions. What are the fermions? They're domain walls of that XY model, right? Sort of transverse domain walls of that XY model.
But is it like if you have a kind of entangled state of bosons and or even a superposition of bosons and fermions, will you get something similar, like a state like composite state of like some excitations which are interacting? I don't know.
So these excitations are in some sense non-interacting. We can ask what you mean by non-interacting, but they're non-interacting in the sense that if you add a particle, the energy cost is always the same, independent of what the other particles are doing. I'm not sure if you can think about it as a composite of fermions and bosons. I think the answer is basically no.
Okay, there is a question, but let's move this to the break.
Sure. Thanks.
So thank Kaden again.